Okay, let's take a look at what's going on here. We have this chemical reaction right here and some stoic problems related to it. Alright, so first off, if 5 moles of Mg3PO4 taken twice are reproduced, how many moles of MgCO3? So now remember, you always start with what you're given, so that determines the first step. And then we want to try to figure out how many, and that's moles. We want to figure out how many moles of MgCO3. So now we're going to the mole-mole ratio. If we have moles Mg3PO4 on the bottom there, we have to have moles Mg3PO4 down here. The 1 comes from the balanced equation, which would be in front of that, which doesn't have a number, but that means that it's a 1, so that's where the 1 came from. And then the MgCO3 is a 3. That's where that came from. Now, the moles MgPO4 will cancel, and we got 5 times 3 divided by 1 equals 15 moles of Mg3. Now, these are shorter because we're starting with moles and ending with moles. The longer problems start with grams and end with grams. We'll be doing one of those here in a minute. All right, the second question, 2.5 moles of H3PO4, so start with what you're given. And then we got moles, so moles H3PO4, so down here we have moles H3PO4. These numbers, 3 and 2, come from the balanced equation. H3PO4 is, where's it here? H3PO4 is a 2, moles of CO2 is a 3, so that's where those came from. 2.5 times 3 divided by 2 equals 3.75. Okay, next, look at number 2. We have our balanced chemical equation. Balanced chemical equation there. And number 3, how many grams of SO2 are needed to react with 3.3 grams Na2SO4. That's what we're going to start with. And we want to end with grams of SO2. So if we have grams Na2SO4 here, we have to have grams Na2SO4 on the bottom. This right here is the molar mass from the periodic table. That always is in reference to just 1 mole. Next, then, we have the mole ratio. If I have moles Na2SO4 here, I have to have that on the bottom. And the thing I'm looking for on the top, moles SO2. And we get the numbers from the balanced equation. Na2SO4 is a 2. SO2 is a 2. 2 to 2 ratio. The last step is to convert the moles of SO2 into grams SO2. So whatever's up here has to be the same thing as down here. And this should be a molar mass from the periodic table. Again, look up S and a couple of O's, add it all together. Then we are ready to calculate. Anything on the top, multiply by it. 3 times 1 times 2 times 64.03 divided by 1 divided by 2 divided by 142.04 equals 1.5 grams of SO2. Grams of SO2. The next question, how many liters if we have 15.5 grams Na2CO3? Start with what you're given, Na2CO3. The very next thing, grams Na2CO3. This is our molar mass from the periodic table. This is the mole ratio. What we started with, what we're looking for. The numbers come from the balanced equation. 2 Na2SO4, 2 moles of CO2. This last factor here now takes our moles of CO2 and converts it into liters of CO2. That's called the molar volume. All right, any of these kind of problems, if they say liters anywhere in the problem, then you know you're going to have to use this factor, 22.4 liters, 1 mole. And that could be 1 mole of anything, really. It has to be gas, but for our purposes, it could be anything at this point. All right, in this case here, it's CO2. All right, so we're using this factor. This will be given during the test. And then we are set to calculate anything on the top, divide by it, anything, or multiply by it, anything in the bottom, divide by it. So we have 15.5 times 1 times 2 times 22.4 divided by 105.99 divided by 2 divided by 1. Of course, you don't have to type in times 1 or divide by 1, but if you do, not a problem. Equals liters of CO2. Number 5, how many grams of this given 15.5 liters of SO2? We're starting with that. Now we have to take our liters, convert it into moles. So now we're using this in this step, converting the liters into moles. In this case, SO2. Moles SO2 on the top, moles SO2 on the bottom. Moles of what we're looking for, Na2SO4. The numbers come from the balanced equation. In this case, Na2SO4, Na2SO4, that has a 2. SO2, that has also a 2. The last step, molar mass, periodic table, converting the moles Na2SO4 into grams Na2SO4. Then we're ready to calculate. Anything on the top, multiply by it. Anything in the bottom, divide by it. So then we have 15.5 times 1 times 2 times 42.04 divided by 22 divided by 2 divided by 1 equals 98.3. Okay, taking a look at number 6. We have, again, we have a chemical reaction here. Already balanced. How many liters of CO, that's carbon monoxide, not cobalt, carbon monoxide. So we have 94 grams of carbon and 22 grams of sulfur dioxide. Those are our two reactants. So how many liters of CO theoretically produced if all the C is used up, carbon? So we'll start with our carbon, 94 grams. Convert to moles, that's from the periodic table, molar mass of carbon. Convert moles of carbon into moles of CO using the mole ratio from the balanced equation. For carbon monoxide, it's a 4. For the carbon, it's a 5. Now, this last step here is to convert the moles of CO into liters of CO. The conversion factor is this 1 mole equals 22.4 liters, which applies to any compound. Technically a gas at certain temperature and pressure, but for our purposes, anything that deals with liters in our problems of stoichiometry, you're going to have to use this factor. All right, anything on the top, multiply by it. Anything in the bottom, divide by it. So 94 times 1 times 4 times 22.4 divided by 1 divided by 5 divided by 12.011. We end up with 140 liters of carbon monoxide. Now that would be true if all 94 grams were reacted. Now, question 7, how many liters of CO would be produced theoretically if all the SO2 was used up? All right, sulfur dioxide. So let's start with the amount of sulfur dioxide we have and see how many liters of CO. So first, convert 2 moles of SO2 using the molar mass from the periodic table. Convert the moles SO2 into moles CO. using the balanced equation and the mole ratios. In the case of carbon monoxide, it's a 4. In the case of sulfur dioxide, it's a 2. Remember, whatever we start with, grams of SO2, that's going to have grams SO2 on the bottom. And moles SO2. So moles SO2 up, moles SO2 down. Moles CO up, moles CO, I did write in there, down. And again, we're using the molar volume, 22.4. Anything on the top, multiply 22 times 1 times 4 times 22.4 divided by 64.06 divided by 2 divided by 1 equals 15.4 liters of CO. Now, we can figure out the limiting reactant here, because here's our two reactants. And these two Stoich problems both end with liters of CO. Since the 22 grams of SO2 can only make 15.4, and this 94 grams of carbon can make 140 liters, then the limiting reactant is the one that gives us the least amount of product. So the limiting reactant is the 22 grams of SO2. And the excess reactant then is the other thing. So number 10, what's the correct theoretical yield? Well, the theoretical yield then will be what the limiting reactant gives us. That's the theoretical yield. Now, when we go and do experiments, sometimes we get more or less than we expect. And in this case, number 11, it says that we only get 0.75 liters of CO, but we were expecting to get 15.4 liters. So the actual that we got divided by the theoretical, what we should have got, times 100 gives us the percent yield. So in this case, we get a lot less than we thought we were going to get. All right, let's take a look at this last one here. We have a chemical reaction involving pentane, C5H12. Now, question number 12 says, how many liters of water could theoretically be produced in this reaction? Now, we have two reactants, and what we'd have to do is figure out which is the limiting reactant. So we start with the pentane, and then we have grams C5H12, and then on the bottom we'll have to have grams C4H12. This is the molar mass from the periodic table. Next step, if I got moles C5H12, I have to have moles C5H12 on the bottom. The 1 and the 6 come from the balanced equation. For water, we have the 6. For C5H12, we have the 1. The last step is to convert it into liters, as they asked us for liters. Anytime we need liters, we got to use this 22.4 liters, putting the mole part on the bottom to match up with the mole of H2O, and we are set to calculate. Anything on the top, multiply by it. 15 times 1 times 6 times 22.4 divided by 1 divided by 1 divided by 72.15. We get 27.9 liters of H2O. Now, we don't necessarily know at this point that that's going to be the limiting reactant or the theoretical yield, so we have to do the other reactant, the 98.2 grams of O2. Next, grams of O2 from the periodic table. That'll convert it into moles. Next, moles O2 on the bottom, moles what we're looking for on the top, H2O. The 6 and the 8 came from the balanced equation. Oxygen is 8. The last step is just like the last step in the previous part. The molar volume, 1 mole on the bottom, 22.4 on the top. Multiply everything on the top, divide by everything on the bottom, and we get 53.2. Now we know which one is the limiting reactant, the one that is the least. 27.9. Notice they both end in liters of H2O. But since this one can only make 27.9, that tells us that the limiting reactant is the C5H12. C5H12. So we can answer the next question. Now, the theoretical yield then depends on the limiting reactant. So whatever one is the smallest, then that's the one we are theoretically going to produce. The other one then is in excess. So limiting is C5H12, excess is O2. All right, the last question is kind of a percent yield. Remember, for percent yield, you would be having the actual yield divided by the theoretical yield, and the actual yield is something we don't know. So we're going to put in an X for that. And the theoretical yield is this 27.9. So we're going to put that there. It would normally be times 100 equals 72.5. But what we need to do is solve for X. That means divide both sides by 100. Multiply both sides by 27.9. So we'll have 72 times 27.9 divided by 100 equals X. X is 20.2 liters. All right, there you go. The practice test. The real test got a lot of similarities. You're just going to be doing a bunch of stoichiometry problems. Maybe asked what is limiting reactant. Maybe asked the percent yield. Things like that. Good luck.